Morning. We're going to start now with lab exercise 5, and we're going to start by, it says step 1, construct the circuit on the circuit board. But before you do that, it's really, you go down to step 2, measure the resistance in the circuit. Now, you must disconnect each of these resistors, so while they're out of the circuit, we're just going to connect, we're just going to see if they're really what they say they are. So there's the first 5.1K resistor, and we're going to measure it and see if it measures what it's supposed to be, and that's, we're setting on ohms, and we've got 5.095K resistor. So that's going to be my one, that's going to be the one at B, and then this will be the one at D, the first one at D. And it measures 5.098. That would be the one right below the D. And then we're going to measure the third one, which is the second one, down after the D. It's going to be 5.1098. So those are our three 5.1K resistors. Then we have the 1K resistor, which is after the B. And there it is, 0.9968. Then we have the 10K, and it is 9.9845. Then we have the 220. Which is 220.42. Okay, now we're going to construct the circuit on the breadboard. So we come in with the plus from our power supply, and we connect the red to the red plus, and connect the black lead to the black to the negative side. So now we have our power connected. Okay. Now if we follow the picture on the next page, we see we have a bunch of jumpers, and we're going to go with those jumpers. So basically we're going to say we come in and we come through the plus lead to a jumper, that's where we're going to measure our current at A. Then we're going to use another jumper from that same point over to an area called a C, where we're going to use another jumper. So we're going to jump over a ways to that area. And then we're going to use another jumper from that same point to a third jumper, to a third place where we're going to put our resistor. So that's going to be our first resistor, our 5.1K. So our 5.1K, the one that we identified as the first one at B, is going to go there. That's going to go from that point to another point just downstream from it. Now this is our jumpering from the A to the B to the 5.1, and then through the 5.1 to the 1K. So now we go over to the 1K, and the 1K is this right here, this resistor right here. So we're going to jumper the 1K, I'm sorry, we're using the D area right first. So this is our we're going to take this one out and we're going to use the, this was our first 5.1K, which was the one at B. The one here is at D is the first one is this first one right here, which is the, this was the one at D, the 5.1 at D. We're going to jumper. This is the one with the 3 jumps. Okay, and then this is the second one. Okay, that's the second one. And this is the 220. Okay, so this is our 220. Now we come over to a tie point. Excuse me, we're going to come over on the other side, this second one. I'm going to measure these again, see which one was which. So this is the 1K, and this is the third one. This is the point at D. So this is the point at D. So this is going to be our common tie point right here for our so this is our circuit as we followed around from the A point, right here's the A point, to the D point, and this goes through the first 5.1K, through the second 5.1K, through the 1K, and this becomes our tie point for our E. Now we come over with the single one, and this is our tie point to our single one. This would be the C. So this is going to be a short jumper. And the reason we do the short jumper is because we want to be able to measure current, and we put that jumper in there so we can measure current at that point. And now we're going to go with our 10K, which I think is this one, measured again. So this is our 10K. This is our one at C. So this is our 10K resistor. And now it comes down into the same row, the negative side of it, as the, this is the negative side. This is our E tie point right here. And then we have our 2 resistors, which is the 5.1. Now we go back, and this is their first 5.1K, which is the one at B. And we jumper over. I've got to get some more jumpers. We jumper over to a third point, which is the B jumper. So we come over to a third point, and this then becomes our B jumper. And then we use another short jumper. We go over to the B jumper, and here's the B jumper. And then we put in the 5.1K. Make sure we got the right resistor again. Check the resistors always before you put them in. Yep, this is our first 5.1. Then we go to this 1K. Check again. I'm using a separate this is the 220, so I got this one in the wrong spot. This one, it should have been the 220, and I got it in the wrong spot, so I think I'm going to go back. This is the 220. Yeah, this is the right one that goes in here. This is the 220. This is the 1K, which goes with the 5.1, the first one at B. Always check. You always have to check. So we've got this one now coming over, and then it goes over to E as well. I'm going to put another jumper in just to come over to the E tie point. Now we've got all these values coming back to this common E. Make sure they're in the same row. And then go from E to our 0 volts. So again, E goes to the 0 volts. Okay, so we've got the circuit connected, I think, correctly. And we'll find out as we go along, because we'll make some calculations as we go along and see if we're correct. So let's look at what they're asking for. First of all, connect an ohm meter and make sure then use the DMM connect to measure the currents at A, B, C, D, and E and record these values. Okay, so now let's do that. A is going to be, so we're going to make sure that we've got 12 volts. So we're going to set up at 12 volts on channel, on the first channel. Channel 1, 12 volts. Okay, so we got 12 volts on channel 1. Turn it on, Ted. On 11.99, 12 volts. So we can measure that and see if we got it with our little meter here. Yep, we do. We got 12 volts. We're all set there. All right, so now we're looking at what? We're looking at current. So we're going to use this meter set up as a current meter to look at current. So I change over to DCI. And I open the circuit at A, which is this point right here, which is what? We're going to measure DCI. We're going to open one lead, open one, put the jumper in, and see if we can get the reading across the two. So let's see what we've got here. See what we got. This is the current at A. Okay, ignore the minus sign. Okay, now let's just look and see if 4 milliamps is correct. So we take our calculator and we look at the circuit, and are we in the ballpark? So let's just look at this. We've got 3 parallel leads, and we've got one at 6.1K. So 1 divided by 6.1 plus 1 divided by 10 equals plus 1 divided by 10.4 equals 1 over, messed it up, we'll go back and do it again. 1 divided by 6.1 equals plus 1 divided by 10 equals plus 1 divided by 10.4 equals 1 over, and that's 2.77 K. So we have 12 divided by 2.77 equals about 4.33, and we got about 4.12, which is very close. So we're in the ballpark. So let's just take that and remember that, and you know, you do your own calculations, but those are close. Okay, so we've got the value at A. This is the value at A, and ignore the minus sign because I could flip the leads around and it would be plus instead of minus. Okay, so now we're going to put this circuit back together at A, and we're going to measure it at B. So now we're going to take this and put it together back again at A. We're going to measure the value at B, which is the value through the 2 resistors. So now we have this jumper here that we can now lift out. See how convenient it is now that we've got all these jumpers in here? So this is the value at the 5.1 and the 1.0. So now I've got my 2 leads, and I put my one side on the one clip and the other on the other, and I make the current go through the meter, and I get what? I get 1.86 milliamps. And let's just see if that's right. So 12, get your calculator, 12 divided by 6.1 is equal to what? 1.96, which is, this is close. It's not exact, but it's close. Okay, so that's our current through B. Now we're going to go to C. Put the jumpers back. You always have to put the jumpers back when you take it out. You got to put the other jumper back very carefully. That's the point at B. Now the C is the single 10K resistor, which is this one right here. So again, we take the one side out, put the other jumper in where we took the one out. And you got to be very careful. You get it in the same row. You got to be real close there. Okay. Now you measure the current there. So this is the current through the 10K. So that's 1.11 or 1.10. So 12 divided by 10 is right about there. Okay, ignore the minus sign. I could flip these leads around and it would all be okay. So that's our current through B. And finally, or excuse me, that was our current through C. And finally our current through D, which is the 3, which is these 3 right here, is this right here. So you notice that this is different than the current at A. This is the current at A. This is the current at B. So we're going to get this little piece right here, and we're going to jumper, take that out, and put this in, measure the current through here. So we force the current to go through our meter for our current readings, okay? Current reading is 1.07. thereabouts, okay? 12 divided by what? 10.4 or thereabouts is right at that. Okay. That's our reading for D. Now that's everything on the plus side. Let's go put it back together again. Got to put the circuit back together correctly. And then we go to E, which is down at the bottom. And here we've got no need for that secondary jumper because we got the jumper that goes from the tie point down to the base where we're doing it. So basically we pull out that jumper, put the jumper in there, and we measure across the E tie point, which is the point where they all come back together again and they go back to the power supply on the negative side, which is again that current right there, which should be about 4.2726, whatever. And that's our current. And the rest of that is what? It's data analysis. So you basically have the values you need to write your report. So hopefully you see how to put this together and okay. All right. So that's the data you need for exercise 5, resistors in parallel. Take care. Okay, we're ready to begin lab exercise number 6. I've gone ahead and built this one, but it was just like the power circuit except for a few changes. So I have the 12 volts here to here. I have the 1K resistor hooked in right here. It's already in. I have the 5.1 from here to here. I have the 330 over here. This is the 330. And across the AB terminals, this is the 1K resistor right there. So I've already set it up, and I'm ready to make the measurements. So it says, first of all, use the DMM to measure the current through each resistor in a circuit. So let's do that. First of all, I want to measure the current into the 1K resistor right here. So I pull, I've got my meter set on amps, so I pull the one side going into the first resistor, put a jumper in, where I pull the resistor, hook the leads to the leads from the meter, and I get a reading 5.6, 5.6. Let it stabilize. 5.46 milliamps in that range. So that's my current at A. Really, it's it's jumping around a little bit. When that happens, you try to see if there's any loose leads or anything that can possibly have gotten loose, and you try to see if there's any way that it's going down. So you try to jiggle all the leads and see if there's a lead that. Now that's a little bit better, because our theoretical value is about 5.6 something. So 5.3, 5.5, that's a little bit better than the prior one. 5.7, 5.8, 5.9. There we go. 5.63, 5.64, 5.65. Use this value for your current 5.65 at A. That's the value going into the that's the value going into the 1K resistor. So now we're going to go back, replace the jumper, and go down and do what? We're going to measure the value of across the 5.1K, which is this resistor right here. In order to do that, I pull one end of the jumper out and put the other jumper in where I pull that one out, and I want to measure the current across these values right here. Okay. So it's a 1.16 something? 1.164. That would be the current through the 5.1K. And the current through the 330, which is also the current through the 1K. So I'm going to pull the one end, put the jumper in, measure the current. This would be the current through the 330 and through the 1K. The current down that leg. And I got the minus sign, I got the leads backwards, but it's 4.54 or thereabouts. So the 4.54 and the current through the 5.1 should add up to the current through the 1K. So that's what we need to know. Okay, so I'm going to put this back. I want to measure the voltage across each of these, so I want to change to DC volts, move my lead back to the top. I want to measure the voltage across the 1K resistor. .66, 5.58, 5 point something. Okay, that's the voltage across the 1K, the voltage across the 5.1K. The voltage across the 330. And you can ignore the minus sign. That's the voltage across the 330, and this is the voltage across the 1K. So now I've got all the step 3 completed. I've got all the voltages and all the currents in this circuit. Now it says to do what? Remove the 1K resistor and measure the Thevenin voltage between points A and B. So I'm going to remove the 1K resistor, pull it out, and now I want to measure the voltage between those 2 points, which would be this point and that point right there. So I'm going to measure the voltage, the Thevenin voltage. This would be V Thevenin with the resistor removed. Here's my voltage, and again you can You can ignore the minus sign. I'll flip the leads around so you can get the without the minus sign. But there's my Thevenin equivalent voltage. Okay. So let's write that down. So turn off and disconnect the power. Turn off the power. Disconnect this. And it says disconnect the power supply and replace it with a short. So I go from the negative to the positive with a short. So I short from negative to positive. And I use my readings up here on ohms. So I look at my ohms looking back into the circuit of my Thevenin equivalent circuit. So I look at my ohms. This was the 1.3582K. So the Thevenin resistance is 1.3582K and Thevenin voltage is 9.81 volts. Okay. So now I want to rebuild a circuit and rebuild it with the 9.81 volts. Let's see if I can even do that. So I need a resistor. Take all these out. Take all these resistors out. And now I see if I can get 9.8 volts. Let's see if I can even get that. Let's try. Maybe I can, maybe I can't, but let's try. Okay. Okay, so that would be my voltage supply. Let's see if I can get 9.8. Okay, so that we've set up at 9.8 volts, and let's just read and see if that's what we got. DC volts. .79, pretty close. 9.8, very close. Okay, so we got our voltage. Now let's see what we got for. We need 1.35K. So let's measure and see if we got a 1K. Let's see if we got any 3.5Ks or anything like that in our. We have a. We have a 3.3K. So we're looking for a. This is 330. So we have a 1K. Let's see what these together look like. So let's put these two together. So 1K. This is a 3.3K, and we want 1.35K, but let's see if we're close. This probably is close. So let's just measure our ohms. So that's 1.336K, and that's pretty close. So let's use that. So let's rebuild our circuit. So now we've got our incoming voltage coming in through the 1K, through the 3.3K. Now this comes to our A terminal. So we're rebuilding our circuit based on the fact that we now have a Thevenin equivalent circuit. So this is our Thevenin equivalent circuit, so it's going to be from there to an A terminal point someplace is this is our A point. Okay, so we're going to now go back and we're going to put our 1K resistor back across there. See if we can find our original 1K resistor. See if we can find which one of these is our 1K resistor. It's our 5.1. I got to go fish here, find the right one. This is our 1K right here. So this is our 1K resistor, and this goes across our output and it goes to the 0 or ground. Okay, so that's, we're going to use a jumper to get it to there, so we're not going to go so far. Okay, so we're going to use a jumper to get there. Now, it says what do we need to do with this? Okay, so we've built our Thevenin equivalent circuit. So this would be our R Thevenin, this is our V Thevenin, here's our V Thevenin, our R Thevenin. Now, if this is true, we should get the same current going through this 1K resistor as we got originally. Okay, it says replace the 1K between the A and B points. Now use the DMM to measure the current and voltage across the 1K resistor and record these values. And let's ask ourselves as we're doing this, should these be the same as they were before? And they should be, but let's just try it. Okay, so let's go to current, DCI, move the meter, leads. We're going to measure the current right here through the circuit. So let's see if this is correct for current, if our current is the same as it was before. So that's our current through our Thevenin equivalent circuit through our 1K resistor. Is that the same? Question, is it the same? You recorded it before. Is it the same? Okay, now that's the current. We're going to put the circuit back, take the jumper. Okay, now we're going to measure the voltage across the resistor. So I move the lead back to the voltage, and I come down here and I measure the voltage across. I hit DC volts, measure the voltage across, and don't pull the resistor out, Ted. Okay, so we do this. Now we see what we got. 0. So there's something missing here. We've got something that's not. There you go. It wasn't connected. Now we got it connected. Let's see what we got. 4.15, 4.14 volts. Is that what we had before? If it is, then we've basically shown through experiment that Thevenin works, that the Thevenin equivalent circuit works. The rest of it is up to you to describe the results. Take care and have a good day. Well, we're talking about lab exercise number 8, an RL circuit with a time constant. So we're looking at a inductor, and I'm going to show you the inductor in a minute, but we previously measured the inductor and we got a value of L is equal to 2.89 henries, and we measured its R value, the R of the L, and it was about 20.8 ohms. So we basically take these two variables with us as we go through the rest of the project. But we're going to hook up a circuit where we have a DC, like a step circuit, positive to negative, and we vary the frequency, and I'm not sure, I think it's 6 volts, but anyway, we got that variable supply. We have an inductor with the R involved with it, then we have a resistor, and we're measuring across the output. Basically, as we measure the voltage across the resistor, we're measuring the current of the, if you divide by 12,000 or 10,000, we're basically measuring the current in the circuit. So this is a 10K resistor, and it was measured at 9.97K. So 9.97K, and this was 2.89 Henry. So our tau, or our L over R, we would expect to be 2.89 divided by 10 to the 4th, or 0.289, approximately 289 milliseconds. So that would give us an idea of our of the amount of time it would go to 67% of its final value. So this would be the time it takes to get to 63% of the final value for that waveform. So we're going to see a waveform that's going to go down and it's going to go up. And when it gets to 63%, that's the value at 63%, we're going to measure this time here and see how long it takes to get to that point. So we're going to look at the circuit, and we're going to try to measure those values and see where we're at. So we're going to move on, and we're going to transition over to that circuit, and we're going to be looking at the values and the so the square wave is on there right now, and it's at 300 hertz, and I've already set that up, but I wanted to show you the square wave, and this would be the square wave on the scope. This would be the square wave on the scope, and I push the little magic button over here to see the square wave, and there it is. That's a square wave. Now we're going to come over here and look at the square wave. So we got a 300 hertz square wave, and here it is over here. Here's our 300 hertz square wave over here. And there it is. And now we're going to look at this, the value after the inductor. This would be where we would see our rise time. So this is our value at the rise time. So now you can look at this value here, and this is the scale. It's from the minimum to the maximum, and I can adjust that down a little bit so we can actually see where we're at. I think this is the value that brings it down. Oops, this one brings it down. So if you can see that hatch mark, maybe you can't see the hatch mark, but there's from where it starts, there's 1, 2, 3, 4, almost 5 hash marks when it goes up. So it goes to about 63% at 1, 2, 3, or right about in here. And each of these hash marks is 500 microseconds, or half a millisecond. So that's from there to there is 0.5 milliseconds. From here to here is 1 millisecond. So 0.2 milliseconds would be, that's 0.5. This would be about 0.2, and it's we see the cutover a little bit more than halfway through this line. So this would be this is 60%, which is really close to 63%, and it's a little over 0.25. Let's just call it 0.275, and that would be very close to 0.289, excuse me. So 0.275 would be our tau, and we would compare that to 0.289, which is the value that we were looking at on this, from a theoretical point of view. So here's the measured tau, the L over R. The calculated one would be 10,000 or 9,970 ohms, which would be our R, and L over R would be 2.89 divided by 9,970 ohms. So that would be our value of that would be the theoretical L over R, and the measured L over R would be the value that would read off the screen, which is 0.275 milliseconds. So our theoretical value would be 0.289 based on the calculations, and the 0.275 would be the value measured off of the oscilloscope. So that's a fairly quick analysis, but that gives you the points that you need to be able to calculate the values that you're being asked for. And it says a table containing the time constant and the measured and calculated inductance values, a brief discussion of your conclusion, and basically the conclusion is that you can look at this exponential rise time for current, and it's almost dead on what you would expect from a theoretical point of view. So take care and have a good day.